Hi, and welcome back to Historical Geology. And today I want to finish up PowerPoint for Chapter 4. And these last couple of parts deal with carbon-14 dating and tree ring or dendrochronology type of dating. Now, for carbon-14 is an isotope of carbon that's continuously being made in the upper atmosphere. And the way it works is we have cosmic rays or cosmic radiation that comes down in the form of protons or electrons or neutrons, and neutrons will essentially bump a proton out of the nucleus of nitrogen-14, because remember, 78% of our atmosphere is nitrogen, so we have lots of this nitrogen. And so if a neutron bumps a proton out of the nucleus of nitrogen-14, what happens, we still have the same atomic mass, but now we've converted a proton to a neutron. So now that means the atomic number must decrease by 1. So remember, the atomic number of nitrogen is 7. Carbon has 6, right? So we lost a proton, so now this becomes carbon-6, but we didn't change the weight because we just replaced that proton with a neutron. So anyways, that's always happened. It's a continuous supply in the atmosphere. And so carbon is a component of carbon dioxide. As long as the plant is alive, it's going to be absorbing carbon that has some carbon-14, right? Most of it's going to be carbon-12, maybe a little bit carbon-13, but most of it is 12. But it will get some of that 14. And as long as it's alive, it's getting a constant supply. Every time it does photosynthesis, it's getting that supply of carbon-14. So in other words, the decay of carbon-14 really cannot be measured until the animal dies, right? Animals who eat the plants, well, they're getting their constant supply, right? So as long as the organism is alive, because it's continuously being formed at a relatively constant rate in the upper atmosphere, every living thing is getting carbon-14. As soon as the organism dies, then the decay process begins. The atomic clock closes, and we begin to accumulate nitrogen-14, because carbon-14 will decay by beta decay back to nitrogen-14. And so that's where the atomic clock begins. So, and then that's how carbon dating works. One important thing about carbon dating, the half-life of carbon-14 is about 5,730 years. And so you really can't date anything older than about maybe 55 to 70,000 years. Some textbooks say 70,000 years, but really it breaks down anything much older than about 55,000 years. So it's really for younger deposits, and like coal or charcoal or bones or something, but something that must have been around in the last 50,000 years or so. So in other words, you cannot use carbon-14 dating on dinosaur bones, because dinosaurs lived millions of years ago, more than 65 million years ago, and carbon-14 doesn't work on anything that old. So it only works on something that's about maybe 50,000 years, 55,000 years and younger. Now, the other method of dating is tree ring dating. And the way tree ring dating works is that each tree ring represents 1 year. So you can literally take a living tree and count basically the rings and figure out how old that tree is. And so by doing that, you can take a living tree and especially some of these like old redwood trees that live for several hundred years, you can count back the tree rings. And one thing you would notice is in these little images, patterns of tree ring growth. There might be really wet years, or maybe where the rings are really close together might be a dry period. And so think of these as like fingerprints or to a climate or a change in the weather during this period of time. In this case, this tree, we're looking back about more than 200 years in this case. And let's say we were looking at an old adobe structure out in the American Southwest, and we want to figure out when the people made this adobe, and then you look at the timbers. So maybe they chopped a tree down, and so if we look at the tree rings in the timber, we see that they match in this region from about 1800 to 1850. So we can get a numerical age using this cross dating or tree ring dating. Another word we have for tree ring dating is called dendrochronology. And it's the same idea here. Here we have a tree that's going to about year 1990, 2000 here, and we can date this living tree going back to about maybe 600 years. So it'd be a tree that's lived over 600 years here. But then we can match it to a tree that probably died about maybe 500 years ago, but then it can be traced back even farther to maybe the year 1100 or so here. And then we find another tree that we can use this to date even farther. So again, we can go back and accurately get ages, in this case over in the year 800, which is over 1200 years from today, from the year 2000. And this technique of dendrochronology can go back to about 14,000 years. Right, the next thing I want to cover is a little bit about the lab, because this week's lab has a little bit of a tricky problem that when I tried it, if you're not familiar with it, it might frustrate you. So I'm going to give you some pointers here. And this first experiment is going to have you count Skittles. And basically you shake them in a cup and you toss them on the table, and the parent atoms are going to be the Skittles that have the S, and some of the Skittles will be upside down. You won't see anything. Those will be your daughter atoms, right? So anyways, you can read the directions on that. But one thing you'll want to read carefully is the pre-lab here. But then they give you this kind of strange equation here on radiometric dating. The other big part of this lab is looking at this table 2. They ask you to, they repeat it again. They repeat it here in the lab, the experiment you're doing. The important thing of table 2 is this gives you the half-lives, right? For the half-life of this system. And so it's 713 million years, right? So it's 0.713 billion, but let's do it in million years. So 713 million, this would be 1300 million. This is 4,500 million. Let's look at what this lab is going to entail. You're going to do these trials. You're going to take some data, right? You're going to make a table. And the key thing about this table, counting your Skittles, you'll find that about half of them will have the S up and about half will have the S down. And then you'll take that parent amount, shake it again, and then you'll see that about half of those will be S up and about half will be daughter. So you'll put the number of S up and the number S down. But the key thing, you want to have a running total of daughter products, the accumulation of the daughter. So in other words, ideally, this number of accumulated daughter products, by the time you get down to trial 6 or 7, this plus whatever you have left in the parent atoms should equal your initial amount of Skittles. Let's say you started with 100 Skittles. By the time you're down here to trial 7 or 8, you may be down to 2 Skittles, which means your cumulative total should be around 98 daughters, right? So 2 plus 98 would give you 100. So over here, what I did on the Doppler camera is looking at this radioactive decay. And remember, parent atoms are said to be radioactive. Daughter atoms are said to be radiogenic. Remember, this means genesis or birth, so they come from radioactivity. Remember, half-life is this time required to decay the parent atoms by 50%. And you'll see that there are several atomic clocks. There's the carbon-14 to nitrogen-14. Remember, it's T1/2. That's its half-life. How long it takes for the parent atom to decay by 1/2 is 5730. There's 235 uranium-207 lead. Its T1/2 is 714 million years. And then there's potassium-argon, T1/2 of 1300 million years. And then the 238 uranium-206 of a T1/2 of 4468 million years. And so essentially what you're going to do, this is not my trial, but I just kind of made up some numbers. I said, well, let's say I had 782 Skittles. So at the beginning, I'm going to have only parent, 0 daughter. And so its age is going to be 0 because it's starting off. So here I've reached that blocking temperature, and I've closed the system, and I'm going to begin the decay process. So after 1 half-life, which is 50%, 0.5 of the sample, I get about half of them a decay to daughter atoms. So I get 391 parent, 391 daughters, right? So note that the column for daughters, I'm doing the accumulation of the daughters, right? So in other words, as I decay the parents, well, those parents turn into daughter product. And so as I go down here, you'll see that after 3 half-lives, I'm about half of 196. Then after 4, I'm half of 98. And anyhow, this just keeps going down by half, and a half, or pretty much close to. And this whole time, the daughter is increasing or accumulating, getting larger and larger. So by my 6th trial here, I have 770 daughter atoms and 12 parent atoms. Well, those together add up to the 782, to my initial amount. Now over here, the equation that they give you in the textbook or in the lab is that the age equals a T1 half, which is a half-life of the sample, which is one of these numbers right here. And what I'm going to do, I'm going to use a uranium-235 system here. So I'm going to use 713 million years, divided by 0.693 times the natural log of the daughter over parent plus 1, right? So I did a couple of these, and I just want to run through one with you. In fact, we'll do this one here at the third half-life. So what we'll do on my phone here, we'll write this equation. So the age of this sample, remember I'm using uranium-235, so it's 714 million years divided by the 0.693 natural log. In this case, now my daughter product is 684, right? Because I want the daughter product divided by the parent, which is 98. Then I add 1 there. So when I do this, this comes out to the age. This, if I do the division here, this is going to be 1030. And then then I'm going to have the natural log of 698 divided by 98. 698 divided by 98. So that gives me 7.122. Now I'm going to add the 1, because I have to add the 1. So that gives me about 8.122. We'll just do 3 significant figures there, right? So that's this here. Now I'm going to take the natural log of that. So I'm just going to hit my natural log button here. And so that becomes 2.09. And I'm going to multiply that by the 1030. So my age is going to be 1030 times 2.09. So times 1030 here. And I get 2158. I'll just round it up. Million years, right? So that number would go right here, 2158. So that's just doing it by using the equation that they gave us. And you can see as well, you can try this next one, but as you go farther along, it's going to get older and older and older, right? All right. So this equation that they give you in the lab. So what I want you to do in the lab, they want you to use uranium-238, but I'd like you to use uranium-235, which has a half-life of 714 million years. And then they want to know how old your sample was at the end. You don't want at the end, because at the end you're going to have 0 parents. It's not going to work. So you want to do it where you still have some parents left. So do it after the 5th trial. And then as we go down in here, for this question 3, the key thing about question 3, for this one, you're going to have to use this equation. The age is T1 half over 0.693 natural log of daughter over parent plus 1. So use that for question 3. For problem 4 down here, now they're saying you want to use a different equation than in the problems 2 and 3 up here. For this one, I want you to use this age equation. The age of the sample would be half-life, which is 714, times the number of half-lives elapsed. In that case, it would be basically the trials. Was it 1, 2, 3, 4? So in this case, they wanted to know after 3 half-lives, so after 3 trials, so it'd be 3 times 714 would give you. And you'll find that the numbers don't match very well, and that's because we're not really dealing with isotopes here. We're dealing with skittles, so it's just a demonstration. So it's not going to be exactly, but we're modeling it using a simple analogy here, in this case skittles. But in the real world, we would be measuring this with a mass spectrometer, and we'd be measuring the isotopes, right? So anyways, that's a little heads up on this experiment.